All right, so for this first one, we have that a medical center is testing patients for a certain disease, and that this disease occurs in 5% of the population. Then they follow up by saying that they test every patient who comes to the center on a particular day. And of course, for part A, to state the sampling method being used. Now, sampling method makes reference to like who do they survey? Okay, who do they test? And so who do they test? They test every patient. All right, so every is a word that's going to help us here. And also on a particular day. So those are two big hints for what sampling method is being used. There's usually around 5 sampling methods, especially at the IP Math AISL level. These are probably the ones you're going to be going through. Those. Okay, we have simple random, convenience, systematic, quota, and stratified. And so simple random in its name, it's kind of like you have a set amount of patients, you pick 10 of them, and you survey those 10. See? So in this case, it's not simple random because we are testing every patient. See, if you're testing every single patient, then it's not simple random. All right. Convenience in this case is correct. It's the easiest path, but you conclude that it's convenience mainly because it's not the other ones. Okay. And so I'll come back to that. All right. But for now, trust me. So it's not simple random because it's testing every single patient. It's not systematic because systematic would be something like, ooh, every 2 patients we test them, or every 3, or every 4, right? But not every single one of them. Quota would be something like you want your sampling method to end up with 30% young patients, 70% old patients. See? So in this case, there's nothing like that. Again, we are testing every single patient that walks through the door. And stratified forces you to split your sample or your population or whatever into groups. Okay, so this usually comes in the form of like, I don't know, like you make a sample with the ones that come in the morning and you make a sample with the ones that come in the afternoon. Okay, that could be a sort of stratified thing. Notice that it's different from quota. All right, the way that they make the groups is different. It's a different sort of criteria, and so it's not stratified. So it has to be convenience. So again, you cannot conclude in this scenario that's convenience by going backwards. You go discarding the ones that are not, and you end up with just convenience. I know that's kind of weird, but it's also because convenience is kind of weird. I mean, the definition of the convenience sampling is like you're literally taking the easiest path. Okay. Um, so you usually reach that conclusion by discarding the other ones. All right. So, anyways, the sampling method being used is the convenience sampling, is what we would answer here. Convenience sampling. Again, you reach this because you are discarding everything else, but it also kind of makes sense. I mean, it's the lazy way. You just test every patient and you just forget about it. It's pretty convenient. Just saying. All right, we keep going. Then they tell us that it is intended that if a patient has the disease, they test positive. If a patient does not have the disease, they test negative. Makes sense. However, the tests are not perfect, and only 99% of people who have the disease test positive. All right, I'm going to take a moment right there. This, that is in purple, okay? So the tests are not perfect. Only 99% of people who have the disease, sorry, 99% of people who have the disease test positive. So have the disease, test positive. That's where this 99% is, okay? Have the disease, bada bim, test positive, bada boom. All right, that's how we got that 99%. So where does this 2% go? They tell us also 2% of people who do not have the disease test positive. I'm going to use another color here so that we know what's going on. I will be using, let's say, red, okay? So 2% of people who do not have the disease test positive. So do not have the disease, so it's going to be this way, test positive. Test positive this way. So that 2% is hidden on C. So this right here is going to be 2%. All right, that doesn't really look like a 2. Let me redraw it. I did about 2%. All right, so that's where this 2% just went. I am just inputting the information that the problem is giving me. You always want to double check that the numbers they give you are actually in your diagram. So the T diagram shows some of this information. See, so we had to fill in the rest of it. And actually for part B, we need to fill out all of it. So for C, we already know that it's 2%, and I should be able to figure out the rest on my own. How do I do that? Well, the cool thing about tree diagrams, or the convenient thing, is that the probabilities add up nicely. What do I mean by this? The probability of any scenario has to be 100%. Okay? Like whether it happens or doesn't happen, you add it up together and it goes to 100%. For example, if you have a disease, there's a 99% chance that you test positive. See? So what's the chance that you test negative? Well, of course, it has to be 1%. Why? Because you're doing 99 plus x has to equal 100%. How do you know that it's 100%? Because this here has to equal 100. This here, also in orange, has to equal 100. And you guessed it, this here in orange also has to equal 100. A very common mistake is that people say this has to equal 100. That is the mistake, okay? It's a very common one, that's why I pointed out. Every set of roots, if you want to call it, okay? Like this would be one root, this is another root, since it is a tree diagram, ¿cierto? Has to equal 100%, all right? So each of those pairs has to equal 100%. Each of my orange circles has to equal 100%. So now that I said that, it's all going to come out very easily. See, for example, for this guy here, I'm going to say, well, 5% plus 8% has to equal 100%. Well, A has to be 95. Boom. If C is 2%, D has to be 98%. And B already did it earlier. See? So again, this part is not particularly hard, but you do have to understand well how the tree diagram works. And the biggest hint I can give you is this thing that I drew in orange. See? What is important about it? Every orange thing equals 100%, and you work from there. Awesome. So we keep going. Part C. Use the tree diagram to find the probability that patients selected at random will do each of these thingies. Okay? So, in probabilities, there's buzzwords that can help a lot. See? These exercises in general, you want to look for buzzwords, and in the realm of probabilities, and is a massive buzzword. Okay? And I'm going to put it in text here. In the world of probabilities, we have that and is going to be a sort of multiply, and we have that or is going to be a sort of add. Okay? Later on, we have given, and it's just kind of like weird shit. But I'll go over that later. ¿Vale? For now, let's focus on and or. So right now we have and. See? So that means we're multiplying. So we'll not have the disease. We said was no disease is A. A is 95%. So I'm looking at this path that I'm going to draw in, let's say, dark blue here. So we're going this path, ¿cierto? Not have the disease is A. A we said it was 95%. So 95%. And, so we put a multiply, we'll test positive. So and we'll test positive this direction. This is the probability we're searching, see? And when I put a circle here, or a square, let's say, it's the probability of going down this purple path, okay? Going down this purple path does not have a probability of 2%. That is another common mistake. The probability of going down that path is multiplying the A times the C, okay, which is in this case 95% times 2%. Now you might be thinking, how the hell do you multiply percentages? Most calculators can just kind of do that, but I'll take a moment to teach you some free math. So 95%, if you put it as a decimal, is 0.95. 2, if you put it as a decimal, is 0.02. What's an easy way to remember this? 1 equals 100% in realm of probabilities. So 50% must equal, you guessed it, 0.5. Okay, and if you remember that, you can kind of reach everything else. See? Not that it showed up here, but if you were to have, say, 0.5%, then in decimals, that would be 0.005. Okay? So notice there what's going on. There's a couple ways to remember this. I prefer to just have this in mind. See? But hey, to each their own. Point is, if you feel weird about multiplying percentages, you can turn them into decimals. Dude, you should even turn it into fractions, my guy. Anyways, you go here, you multiply these two bad guys, and you end up with 0.019. If you don't like how this looks, then you can change it to percent by multiplying it by 100. You end up with 1.9%. Okay, so that is the probability that you will not have the disease and you tested positive. For the second part, we have that you will test negative. And so if you will test negative, there are two options. See? Let me erase what's going on here for a second. Make a little bit more space. So we're looking at will test negative. So in which scenarios, this is how you approach, in which scenarios do you test negative? I test negative here, and I test negative here. Well, all right, tell me more. How do you reach the first one? You reach the first one by first going through disease. So I am doing this times this. 5% times B percent. See? And for the second one, we are going through test negative and no disease. So we're going through A percent times D percent. See? And I add both. I'm going to go over in a second why you're adding both. So remember when I said that and is multiply and or is add? Well, if you will test negative, then there are two options, right? Either you, actually I'm going to do it up here. If you test negative, there are two options. You either have disease and test negative, or no disease and test negative. So those are the two options for when you test negative, right? You have the disease and you test negative, or you have no disease and you test negative. So, just to make it more visual, disease. There it is. And there's a multiply. Test negative. The B right there. Or we put the add. No disease is A. And there's the multiply. Test negative, the D. So that is why we're adding, and that's why we're multiplying these scenarios. You have to think in terms of and or ors. So scenarios where you test negative are those. Okay, so I'm going to plug in what I have in yellow over here. It's going to look something like this. We have 5% we said was 0.05 times testing negative B, which we said was 1%, so 0.01. All of this being added, ¿cierto? To the alternative, which is A times D, ¿cierto? We said A was 95%, and we said that D was 98%. So all of this into your trusty rusty calculator, and you're going to end up with 0.9315. All right? If you don't like how that looks, you turn it into a percent. That is 93.15%. So this is probability of testing negative. That is for the second part. See? All right, awesome. Oh, just to write it down, here we said it was 1.9%. And will test negative, we just said is 93.15. 15%. Right, and now for the third part, we have has the disease given that they tested negative. So now that we're in the given land, we are into the weird shit section of the world of probabilities. And so given has a particular approach, okay, and it's so flippin' weird that it's in the formula booklet. And you know it's weird if it's in the formula booklet. And so your formula booklet has conditional probability, which is also for given. Okay, so when you see the word given, you have to think conditional probability. It is this guy here. Okay, and so the way you read this is probability of A given B equals that whole thing. Okay, so probability of A given B equals that. Okay, the formula. Point is, this line here is your given. Okay. All right. Anyways, so that is where I'm getting this formula from, just so that you know. And so if I go back to my tree diagram thing, we have has the disease given that they tested negative. And so we said it was P A given B equals P A and B. And on the bottom we have just P and B. And so the hard part here is defining what is A and what is B, and you work from there. Now, we said that it was A given B. And so A is before B in the word given. So anything to the left of given is going to be A. And anything to the right of given is going to be B. And so A and B is going to be has disease and tested negative. So has disease and tested negative, which is actually what we did for part A. So part A is exactly that. For part A, we found that we had to do 0.05 times 0.01. Okay, so that right now is plugging in for P, A, and B. All right. And on the bottom, which is probability of just B, we have that they tested negative. What are the scenarios where they tested negative? We have the scenario that goes like this, tested negative, and we have the scenario that goes like this. They also tested negative. Whoops, sorry about that. They also tested negative going through this path here, which is actually what we did for part B. And we saw that we had to do A times A times D plus 5% times B. See? So if I write it out real quick, we end up with, on the bottom, 0.05 times 0.01 plus 0.95 times 0.98. All right. So this is pretty consistent from what we did in this first part and the second part. They both sort of like combined onto the third one. All right, which is actually, side note, pretty useful for IB. IB in general is like, for the third part, you probably need something from the second one or the first. Okay, for part C, you probably need something from part A, from part B or part A. Okay, that is a very common trend and can be a big hint on how to approach what's coming. So that being said, that is how you plug into the formula. See, so probability of A and B is what we have on top. Probability of B is what we have on the bottom. This is literally what the formula is asking for. The hardest part is identifying what is A and what is B. Again, the buzzwords are huge. That's why I wrote the buzzwords over here. We have and, or, and given. Okay, those are our buzzwords. You gotta search for them, and that is your compass on how to approach these things. You plug everything into your calculator, and the probability of A given B, in other words, has the C's, given that they tested negative, is going to be just around 0.000536768. If you don't like that number, I want to turn it into decimal. That would be 0.0537%, let's say. Okay, so again, either of these works. That is the answer for this third part. Then they tell us that the medical center finds the actual number of positive results, because again, these are just probabilities, but the actual number of positive results in their sample is different than the predicted by the tree diagram, and we need to explain why this might be the case. Now, for these scenarios, there are a lot of different explanations that you can give. The most direct one, I think, is that the sample for convenience, as we said earlier, because it's the easiest path, the easiest path is usually not the best path, unfortunately. Okay, so you can immediately say that because the sampling method being used is convenience, then, the sample is not representative. So you can actually say that. You can say here, sampling not representative, convenience, sampling sucks. You would use other words, but that's the main idea. Okay, you can also say sampling is not random, which is another way to say that it's not representative. Okay, and you can also simply say that, hey, the medical center is comparing observed versus expected, and it's very common for your observed values to be different to your expected. All right, the answer key does have it like this. Okay, so just so that we're all on the same page, either one of these three is going to work. It's exactly what I just told you just now. But at the end of the day, the intuition is like you gotta hammer down on what's the sampling method, or also just say like in theory, the observed and expected is not necessarily gonna be in line. Okay. All right. Awesome. So either one of those is gonna grant you that 1 point. That is for part D. All right, and for this next part, they actually vomit like a lot of information, and they tell us that the staff at the medical center looked at the care received by all visiting patients on a randomly chosen day, and that all the patients received at least one of these services. They had medical tests M, seen by nurse N, and seen by doctor D. And then they give us like a lot of numbers, okay? A lot of scenarios, a lot of numbers, and they give us the mission to draw a party, see, draw a Venn diagram to illustrate this information, placing all relevant information on the diagram. So first things first, how many circles do we have? We have 3. How do I know? Because we have M, medical tests, N, nurse, and D, doctor. So now I'm going to go ahead and draw my Venn diagram. Make it nice and big, give yourself a lot of space. I'm going to put a circle up here for D, doctor. Another circle over here for M, medical, where the hell, medical tests. And N for nurse down here. All right. And so first I'm going to commit a mistake filling in the Venn diagram. Okay. And I want you to really think about what is the mistake that I'm doing with my approach. Okay. So what a lot of people do right off the bat is that they see, okay, 78 have medical tests. So I'm going to put medical tests down here. We have 78. Then we have 45 were seen by a nurse. 45 over here. And 30 were seen by a doctor. 30 over here. So a lot of people, that's boom, the first thing they do. And that is unfortunately already a mistake. So take a moment and think why. For example, 478 had medical tests. It doesn't say 78 had medical tests only, which can be a scenario, ¿cierto? But it doesn't say only. It says that 78 had medical tests. And so that 78, where is it in my diagram? That 78 is actually all of this. 78 is inside all of that, and this 78 that I wrote in, I'm going to highlight in red here, the way I put it in, which was the mistake, is that I thought it was only there. See, but that 78 is actually encapsulated in all of the yellow, not in all of the red. So that is a very common mistake people do when approaching these problems. If it said only, I would be correct in putting it in red. But since it doesn't say only, you actually have to kind of go like discarding from that 78 and see how much were actually only medical tests. So let's take that approach again. I'm going to erase my 78. I'm going to erase my 45, erase my 30, erase that highlighted thing, draw this again. And now that we have that knowledge, we will approach differently. See? And so yes, 78 have medical tests, but for now we're going to put these 3 on hold. Okay, it's useful information, but we do not plug it in right away. We had that 9 had medical tests and were seen by a doctor and the nurse. And so there's a lot of ands there. So 9 had medical tests and seen by doctor and the nurse. This is one thing that I can plug in directly. So this 9 can actually go here. And that actually already tells me that the 78 I had before needs to get subtracted by 9. The 30 that I have for doctor needs to be subtracted by 9. And the 45 that I have for nurse has to be subtracted by 9. And so you go subtracting until you reach the appropriate amount anywhere. 18 had medical tests and were seen by a doctor, but were not seen by a nurse. So 18 had medical tests, so that would be M here, and were seen by a doctor, but not by a nurse. So medical test, doctor, not nurse, it's going to be this guy here. So that guy there, we just said was 18. Bada bim, bada boom. 11, oh, sorry, and now that we said 18, over there, I actually have to subtract 18 from here and from here. Why? Because that 30 and that 78 is either only doctor or only medical check. Aha, now it's starting to make more sense. For this 11, we have that 11 patients were seen by a nurse and had medical tests, but were not seen by a doctor. So not seen by doctor, but had medical and nurse, it's going to be this guy here. We said that it was 11, so we put 11 here. And again, we subtract 11 from both. Why do we subtract 11 from both? Because that 45 and that 78 is only nurse and only medical check, respectively. We move on. 2 patients were seen by a doctor without being seen by a nurse and without having medical tests. So 2 patients were seen by a doctor without being seen by a nurse and without having medical tests. So that means that this guy here for doctor has to be 2. So 30 minus 9 minus 18, does that equal 2? Let's find out. So 30 minus 9 minus 18 is the same as writing 30 minus 27 equals 3. So if I'm missing 1, to reach that 2, I can also just say that it's 30 minus 9 minus 18 minus something has to give me 2. What is that something? It is this guy here. That guy there has to be equal to 1. Don't believe me? From here, we have 30 minus 27 minus x needs to equal 2. So 3 minus x equals 2. Whoops, equals 2. We have plus x to both sides, so we have 2 plus x. We have minus 2 minus 2, x equals 1. So this x here has to equal to 1. This guy here has to equal to 1. And so that, this whole thing here has to equal 2. And so that is the approach that you do to these kind of things. For this 78, if I do 78 minus 9 minus 18 minus 11, I end up with 78 minus, I can't math right now, minus 38. That gives me 40. All right, so this guy up here is going to be 40. And 45 minus 9 minus 11. It's going to be the same as 45. Oh, and also minus 1. I missed this minus 1 here because of this guy. My bad. So we have 45 minus 9 minus 11 minus 1. It's going to be 45 minus 21 is going to give 24. So this whole guy right here is 24. And that, ladies and gentlemen, is the Venn diagram that we're going for. And so again, the biggest mistake most people do is assuming that 78 have medical tests is medical tests only. You cannot assume that unless it says it. Okay, if it doesn't say it, you need to go subtracting from that 78, given the other information that they give us, and you kind of work from there. Okay, that's also why the IB trickily puts this first to try to make you fall into that trap. So careful, be very careful. That is for part E. We drew the Venn diagram, there it is. Part F is find the total number of patients who visited the center during this day. All you have to do there is add all of these guys up. So we have 2 plus 1 plus 18 plus 9 plus 40 plus 11 plus 24. You put all of that into your calculator. You end up with 105. So all of my guys added up together give me 105. That is for part F and for part 1.